Hey guys, so I'm shooting a test 2 wrapper for Professor Kim's Physics 2 class, spring 2014. And on the test 2, I really struggled with problem 1, so I'm going to go through that one. So the first problem says, an electron is traveling with speed 3.2 e to the 5th meters per second in the negative x direction. What are the magnitude and direction of the magnetic field due to this particle at location A? So here we can see a diagram, and we can see that we're given the velocity, which is negative 3.2 e fifth, comma 0, comma 0, because it's going to the negative x direction. And the charge, because it's an electron, is negative 1.6 e negative 19 coulombs. So the first thing we have to do is find our position vector, which is r, and it's pretty easy to find. It's just based on the angle, so we do 5e negative 6 cosine 30 for the x, and 5e negative 6 sine 30 for the y. And because we do that, our magnitude is 5e negative 6, and you can see that our r hat is cosine theta negative sine theta 0. And the reason we need our r hat is because it all comes back to the magnetic field equation, which says that magnetic field is equal to this constant, mu naught over 4 pi, and then times q, velocity vector cross r hat all over r mag squared. So when we look at it, the first thing we have to do is we have to write it all out, and then we cross the velocity, which is negative 3.2 e fifth, and we cross that with the r hat. And when we do that, the only position that actually equates to anything, because there's a lot of zeros, is the z direction. So when we do that, we multiply negative 3.2 e fifth and negative sine 30, because that's our angle, is 30, so that gets replaced by the theta. And when we do that, we get, we multiply that by 1.6 e negative 19 and 1 e negative 7. And don't forget about that negative on the 1.6 e negative 19. So that's 3 negatives in total. So we know our direction is going to be negative. So we went ahead and just put that 0, 0, negative 1. And we went ahead and made our magnitude over there positive, which is 2.56 e negative 21. And then we have taken into account the r mag squared. So we do that. And so that gives us a magnitude of 1.024 e negative 10th Teslas for the magnetic field, and then the direction is 0, 0, negative 1, which is basically into the page, into the z direction. And that's part A of the problem. Hey guys, so part B isn't really related to part A in the problem, but it says 3 metal plates are arranged as shown in the diagram. A small hole in the middle of the plates allows an electron to pass through. Each plate is held apart by insulating supports, which aren't shown, and each has an area of 1.8 meters squared. Each plate is 0.02 millimeters thick. Distance d1 equals 13 millimeters, d2 equals 7 millimeters. The charge q1 equals 2 e negative 7 coulombs, and charge q2 equals 4 e negative 8 coulombs. There's a uniform distribution of charges. So the first part B, says to calculate the potential difference Vd minus Va. And we have our diagram right here. So when you look at Vd minus Va, it's pretty much a potential difference, but it's a net potential difference, so you have to split up into the 3 parts. So here we can see we have Vd to Vc, Vc to Vb, and Vb to Va. Or I guess vice versa, it would be Va to Vb, Vb to Vc, Vc to Vd, but it's final minus initial. So we can do it here, and we look at this, and we show the integral step for the first part, Vd minus Vc. The next 2 parts are really similar, but so we see that we take this integral, and we know that we can equate this to q2 over a all over epsilon naught, and in this case it's negative because if you take into account the direction, as you can see in the top right, and so here we have negative q2 over a all over epsilon d2, and that just equals negative 17.6. Here we go to the second part, Vc minus Vb, and that equals 0 because, as you can see, that's actually the capacitor itself, and since it's metal, it's not going to have a potential difference inside of it. And then Vb minus Va is used in a very similar way, except that it's positive, and the answer for that is 163.2, and then you add those 3 numbers together and you get 145.6, and that's your potential difference. And then part C in this problem says to determine change in kinetic energy as the electron moves from A to D. And so here we can go back to our conservation of energy, and we know that delta K plus delta E equals 0. So therefore delta K is going to equal negative potential energy, we know that potential energy is also equal to Q delta V, so if it's going to be negative Q delta V in this case, and then we do delta K, we set it equal to the charge of the electron times the potential difference, and since there's a double negative, it's going to be a positive change in kinetic energy, and that change is 2.33 E negative 17 joules. Thanks for watching, guys. Once again, my name is Sagar Patani, and thank you. Bye.